Hey everyone, today we're going to talk about the pressure volume loop of the left ventricle, which is the relationship between pressure and volume. So it reflects left ventricular compliance, and compliance is volume change per pressure change, which also reflects the workload of the left ventricle. Now, when we talk about the pressure volume loop of the left ventricle, it helps us understand three variables that reflect heart function or involved in heart function, and these are preload, afterload, and contractility. And by understanding the pressure volume relationship, we can also understand how preload, afterload, and contractility affect it, and we can apply it to the real world. So let's draw a normal pressure volume loop of the left ventricle. So on our y-axis, we're going to draw pressure, and this is in millimeters of mercury, and the two important points I'm going to mark here is 80 and 120, which is normal blood pressure 120 over 80. Then on the x-axis, we're going to draw left ventricular volume, which is in mil, and the important numbers is 50 and 120. So I'll draw a loop here, and let's label it. So at point A, this is mitral valve opens. Okay, so we're at end systolic volume, so the ventricle is just contracted all the way, and there's about 50 ml of blood left in the ventricle. Now the ventricle is filling as the mitral valve is open. So A to B is ventricular filling during diastole. You can see that pressure slowly builds up as the ventricle fills, and it will get to a point now where the ventricle begins to contract. So the mitral valve closes at point B, and B to C represents isovolumetric contraction. So essentially volume doesn't change, pressure is building up during contraction. And then at C, the aortic valve opens, which marks the start of ejection or the start of systolic ejection. So now C to D is ventricular ejection. You can see that pressure is building up, but volume of the left ventricle is going down. So the ventricle is emptying itself into the aorta. Then at D, the aortic valve closes, and you can note that it just drops below the systolic blood pressure of 120. So now aortic pressure is greater than left ventricular pressure, so the aortic valve closes. At this point, isovolumetric relaxation begins, which means that there's no volume change, but the ventricle relaxes. You can see that there's rapid drop in pressure back down to A, and then the cycle repeats itself. So I've already sort of mentioned it, but 80 is our diastolic blood pressure and 120 is our systolic blood pressure. The difference between 50 and 120 mil is our stroke volume. So 120 mil is our end diastolic volume, and the 50 is the end systolic volume. So now that we've drawn a normal pressure volume relationship, let's talk about the different parts of the pressure volume relationship that determine the shape of this curve. So the first one is preload, and preload is the initial stretch of cardiac fibers before contraction, and represents the Frank-Starling mechanism of the heart, which essentially describes that up to a certain point, if the myocyte stretches, it'll reach a point where the contractility or the ability of the myocyte to contract will decrease once it's overstretched, which the classic analogy used is a rubber band, that if you stretch it within the right range, it'll return to its normal shape. But if you overstretch it, it will then lose its stretch and lose its contractility, which also happens to the heart. And this is represented by the end diastolic pressure volume relationship, which is the blue line here. And you can notice that as the volume fills to a certain point, then pressure will begin to rapidly fill, and eventually you get a point where the line is almost vertical, where you can't fill the ventricle any further, it's not going to fill, and the pressure just continues to build, which will affect the ventricle's ability to contract. The next is contractility, which is represented by the end systolic pressure volume relationship, and this is the intrinsic stretch of the myocardium independent of external conditions. Lastly is afterload, and afterload is the external load or work that needs to be overcome before the myocyte or the muscle will shorten. So our first variable we're going to talk about is preload. So preload is represented by our end diastolic volume, So a low end diastolic volume is low preload, and a high end diastolic volume is high preload. Now, when we talk about afterload, when afterload line is parallel to the other afterload lines, it means that afterload has not changed. It just moves because afterload has to commence at the end diastolic volume, and it's a diagonal line that goes up towards the y-axis. And the point at which it crosses the end systolic pressure-volume relationship, which represents contractility, is the point where the aortic valve will close. So now if we draw it for end diastolic volume that's low, we can see that the line, it moves along our end diastolic pressure-volume relationship line. It goes up, hits our diastolic blood pressure, aortic valve opens, ejection commences. As the ventricle empties, at the point where the afterload line crosses the end systolic pressure-volume relationship line, our aortic valve closes. And this is isovolumetric relaxation now. And now if we draw it for our increased preload, we can see that at the point where our end diastolic pressure-volume relationship line crosses our end diastolic volume, the ventricle has now commenced its isovolumetric contraction, so pressure builds up at the level of diastolic blood pressure, aortic valve opens, ejection commences. There's quite a large volume that's being ejected, so our systolic blood pressure is probably higher, and it ejects out and goes above our systolic blood pressure line, which is 120. At the point where afterload crosses our end systolic pressure-volume relationship line, the aortic valve closes, and this is isovolumetric relaxation as pressure drops, goes back down. At the point where it hits the end diastolic pressure-volume relationship, mitral valve opens and ventricular filling occurs. Now you can see here, if I just get rid of a few lines, that our stroke volume is affected. As with low end diastolic volume, our stroke volume was less. And this is with all other parameters being the same. And for our high end diastolic volume, our stroke volume has increased. Now, just a point of possible error on this graph that I just want to point out is that with the low end diastolic volume, I've drawn the line so it goes up to a systolic blood pressure of 120. In reality, it will probably be lower. It'll probably be around 100. But the rest of the graph is consistent and true. So let's talk about afterload now. So before I mentioned that if the lines are parallel for afterload, then afterload's unchanged. But really, when we talk about this graph and with afterload changing, what we're talking about is the angle of those lines. So as the angle becomes less steep, our total peripheral resistance is decreased. So the pressure that the resistance that our ventricle has to pump against is less. And as this angle is more steep, the total peripheral resistance is higher. And this is important because, like we said before, where afterload crosses our end systolic pressure-volume relationship is where the aortic valve closes, which will determine how much is ejected from the ventricle. So let's draw our first one, which is going to be with a low total peripheral resistance, so a low afterload. So at the point where our aortic valve closes, let's start there, where it crosses the end systolic pressure-volume relationship line, which is contractility. Isovolumetric relaxation commences. At the point where it hits the end diastolic pressure-volume relationship, our filling begins as mitral valve opens. We fill up to our end diastolic volume. Remember, preload is unchanged. And now mitral valve closes and isovolumetric contraction occurs. Once pressure gets above diastolic blood pressure, aortic valve opens. And then you'll eject all the way until you get to the point where it crosses our end systolic pressure-volume relationship curve. Now let's do it for a high afterload. So for high afterload, again, we'll start at where it crosses the end systolic pressure volume relationship curve. Pressure drops. We hit our end diastolic pressure volume relationship and filling begins. We then increase our pressure at our end diastolic pressure or end diastolic volume. And again, we get above our diastolic blood pressure and the valve will open. And because afterload is high, our diastolic blood pressure is going to be higher. So blood pressure is increased. So that initial opening of the aortic valve happens at a higher pressure. And you have a higher systolic blood pressure here as well. Now, if all other parameters are kept the same, we can see here that at a low total peripheral resistance or a low afterload, our stroke volume is higher, which makes sense because there's less force that the ventricle has to contract against. And then at a higher afterload, our stroke volume is less. Now, lastly, we'll talk about contractility. And the contractility line here is represented in green. And we usually draw it at the start of the end diastolic pressure volume relationship line. And it's the angle of the line that determines contractility. And the line is known as the end systolic pressure volume relationship. So if we draw the line as less steep, this would be decreased contractility. And the more steep it is, there's higher contractility. And all other parameters are kept the same. So again, the important point here is where the afterload crosses the contractility line or the end systolic pressure volume relationship line, which represents aortic valve closing. And this is isovolumetric relaxation, so pressure drops, hits our end diastolic pressure volume relationship line. We move along that line until we get it to our end diastolic volume. Then isovolumetric contraction occurs. The aortic valve opens once we hit diastolic blood pressure. Ejection begins. And then at the point where the afterload crosses the end systolic pressure volume relationship line with the decreased contractility is the point where the aortic valve closes and then pressure drops. And then again, the same occurs for our increased contractility with the steeper line. And then as expected, our stroke volume changes. So with a decreased contractility, there's less stroke volume, and with an increased contractility, there's more stroke volume. So at the start of the video, I mentioned that this also represents work of the heart. So the area within the pressure volume loop represents the stroke work or the mechanical energy done by the heart during a single contraction. And this represents the external work of the ventricle. And during isovolumetric contraction, pressure develops within the ventricle. Although there is no ejection and therefore no external work, energy is expended to generate potential energy, and this is converted to heat during diastole. The triangle formed by the end of systolic pressure line and the end diastolic pressure line and the line representing isovolumetric relaxation represents internal work, and this correlates the heat generated by the heart during a single contraction. The total mechanical work plus the heat generated by the heart during contraction is represented by the pressure volume area, which is represented as stroke work here. And the pressure volume area correlates well with the amount of oxygen consumed by the myocardium during a single contraction. And when the pressure volume area is extrapolated to zero pressure, myocardial oxygen consumption is still present, and this basal oxygen consumption in the absence of pressure development is required to keep the cells alive. The activation energy is required for the biochemical processes associated with excitation-contraction coupling. So this is a crash course in the pressure volume loop of the left ventricle, and hopefully it's explained it in simple terms that are more easily understood, but you can go into more depth with these and you can change multiple parameters to figure out stroke volume and what happens to the heart. If there's any questions, anything that you want to ask, feel free to ask it in the comments.